So, hello everyone again. This is lecture number 4 part 1 of semiconductor electronics, materials, devices and simple circuits. Let's start our discussion again from the thing we left in the lecture 3, which was extrinsic semiconductors. So, as far as I remember, the last concept was based upon we devised the formula, that is Ne into Nh is equal to Ni square. So, let us look forward one of the simple example related to it, and then we can move on to the PN junction concept. Okay. So, I am Sameer Lavankar. Let us begin our discussion. Okay, so right now we are on the fourth topic, that is extrinsic semiconductors. After this is completed, we will start with a new concept which is called as PN junction. So, PN junction is nothing but accumulation of your these two concepts joined together. Okay, so we will understand basically the concept which we understood, that is P junction and N junction, P type semiconductor and N type semiconductor will be utilized directly in your PN junction. Okay. So, just an outline before. So, we started the introduction, as in we understood about the cathode ray tubes, then we understood about how modern IC chips are being made, then what is the difference between the cathode ray tube and your this modern days IC chips. Then the classification of metals, semiconductors and conductors, we understood several important concepts such as valence band, conduction band, etc. Then we understood different variations or different ways to classify metals, conductors and semiconductors. We also understood the energy band theory in this. Finally, then we went on to understand the concept of intrinsic semiconductors, and then finally extrinsic semiconductors. Okay. So, we got to know the concept, what is a hole, what is a major carrier charge concentration and minority charge carrier concentrations. Okay. So, let us go on to with extrinsic semiconductors final concepts, and then we can move on to the PN junction. Okay. Fine. So, we started with this extrinsic semiconductors concept. Okay. So, in extrinsic semiconductors, we first got to know that there can be two types of dopants. So, one is pentavalent, that is in the valency is 5, and second is trivalent, as in the valency is 3. Okay. Then we understood. So, N type semiconductor. So, N type semiconductor, as the name suggests, if we need to remember it. So, N is basically negative, we can understand N as negative, and what is basically having. So, a negative charge is being added up. So, if a negative charge is being added up, what we can say is it is an N type semiconductor. So, what is basically happening here, a pentavalent impurity is being added upon in this type of extrinsic semiconductor. Okay. Then when this was completed, we went on to understand. Okay, so one of the important thing which we need to consider here is that Ne should be greater than Nh. Okay, that is the number of electrons are the majority carriers and the holes are the minority carriers. Fine. Then next thing is we went on to understand P type semiconductors, as the name suggests, again how to remember this. So, as it is written P can be understood as positive, therefore, here a hole would be present. Okay. So, basically a trivalent impurity has been added upon in the place of your +4 valence of silicon or germanium, and hence that type of semiconductor which is obtained is called as your P type semiconductor, which is a type of your extrinsic semiconductor only. So, here holes are the majority carriers. So, you need to remember this here again. So, basically holes are the majority carriers and electrons are the minority carriers. Therefore, finally what we obtain is that Nh is greater than Ne. Fine. So, these all things are explained, these all things were also explained to you, and finally what we got is that in thermal equilibrium Ne multiplied by Nh is equal to Ni square. So, please remember this formula very clearly because this can be implied in many of the several concepts which we will understand further. So, basically Ne multiplied by Nh. So, Ne, that is the number of electrons into number of holes, should be equal to Ni squared. Okay. So, what is Ni here? Please remember what is Ni. Ni is basically the intrinsic concentration. Okay. So, this is your intrinsic concentration. Fine. So, that being said, then final, okay, let us start the discussion from here onwards then. So, the difference in, I think this was also completed, but let us begin again. So, the difference in the resistivity of carbon, silicon and germanium depends upon the energy gap. Quite evident, it depends upon the energy gap between their conduction and the valence band. So, please remember that this is the conduction band here and this is the valence band here, right. So, for carbon what happens? For carbon, let us take example of carbonized diamond, silicon and germanium, the energy gaps are given here. So, it is 5.4 electron volts, 1.1 electron volts and 0.7 electron volts. As can be seen clearly that it is very high for your silicon, sorry, for a carbon, and then it ranges, the amount of decrease in the energy gap is very huge when you went to semiconductors such as silicon and germanium, and as you can see it is very less for your germanium semiconductor. Okay. So, Sn is the next element which is on the same periodic is in the same group. So, Sn is also a group for element, but it is a metal. Why it is a metal? Because the energy gap is 0 electron volts. Okay. So, it reduces so much small extent that the energy gap becomes equal to 0 electron volts, and because it is 0 electron volts, it is said to be a metal and not a semiconductor. So, these all concepts we also devised when we were understanding the concept of classification between metals, semiconductors and insulators. Okay. So, we understood there also that if the value of Eg is equal to 0 electron volt, that is basically the, let me devise it again. So, we understood this concept there. Let us say that if Eg, what is Eg basically? Eg is an energy gap. Okay. So, if energy gap is equal to 0 electron volts, or else what we can say that the valence band and conduction band overlaps on each other. Okay. Valence band and conduction band overlaps on each other. Fine. So, that are basically those are called as your metals. Okay. And then if the energy gap is somewhat let us say the range was given there, but let us say it is approximately, let us say 1.1 to 0.7 electron volts, then these are called as your semiconductor devices, semiconductors. Okay. So, semiconductors we understood as two basically, one was your extrinsic semiconductor, second was your intrinsic semiconductor, and finally, if Eg value is very high, then all these electron volts given, then those are basically your insulators. Okay. Or what we can say except about more about this, that the valence band and conduction band are very far. Valence band and conduction band are far from each other, are very far from each other. Okay. So, valence band and conduction band are very far from each other. So, that is how we define different concepts such as metals, semiconductors and insulators. Fine. That being said, let us look at the example regarding the formula, that is Ne into Nh is equal to Ni square. Okay. So, let us understand that concept here. So, suppose a pure silicon crystal has 5 into 10 to the power 28 atoms per meter cube. What does it mean? So, basically let us say that this let us say this is the volume we are talking about. Okay. Let me make it much more clearly. Okay. So, let us say this is 1, this is also 1 and this is also 1. That makes it the volume is equal to nothing but 1 multiplied by 1 multiplied by 1, which is 1 meter cube, correct. So, what they are saying is, let us suppose this is a crystal of silicon. So, this has basically 5 into 10 to the power 28 atoms. Okay. So, that is given in the question. Now, next thing is said that it is doped by 1 ppm concentration of pentavalent arsenic. Okay. So, arsenic has been added 1 ppm. What does it mean by 1 ppm? That for every 10 to the power 6 atoms, we have added one amount of pentavalent arsenic. Okay. So, the question is just asked that calculate the number of electrons and holes. Okay. So, you just need to calculate the value of NH and Ne. Okay. It is given in the question that the intrinsic concentration is Ni, which is equal to 1.5 into 10 to the power 16 per meter cube. Okay. So, let us look at the solution here. So, note that the thermally generated electrons, that is approximately Ni as 10 to the power 16. So, it is just giving you the order, are negligibly small as compared to those produced by doping. Therefore, what we can say that N is approximately equal to Nd here. Okay. So, what we can just say simply that here the amount of number of electrons can be said as equal to the amount of number of this amount of atoms here. Okay. Therefore, just dividing it by 10 to the power 6 will give you the concentration of pentavalent the number of electrons. Let me explain it again. So, this may be quite tricky here. So, let us understand again. So, basically what it is trying to say, first of all we know the formula, that is Ne multiplied by NH is nothing but equal to Ni square. Fine. You know the value, what is the thing required here? You just need to calculate the number of electrons and number of holes, correct. If you know the number of electrons, we can just use the formula and find out the number of holes here, right. So, what they are saying is because thermally generated electrons are negligibly small as compared to those produced by doping. Okay. So, because their electrons are very small, what the assumption is being done, this is assumed that number of electrons is approximately equal to number of electrons which is produced by doping. So, what are all the electrons which can be produced by doping? As you know that by doping the electrons can be produced. So, the amount of concentration of pentavalent arsenic we added is equal to the amount of electrons which we will get, correct. So, if that is the case being assumed here, then what we can say that, let us say that if every 10 to the power 6 atoms, for every 10 to the power 6 atoms we have added one crystal or one atom of your pentavalent arsenic, then for 5 into 10 to the power 28 atoms how many electrons would be appearing, right. So, this is basically atoms, and here it is assumed that this atom is also equal to electron. Okay. Therefore, the amount of atoms which is also equal to electron will be 5 into 10 to the power 28 divided by 10 to the power 6. Okay. So, it is simple unitary method which I adopted here, therefore, this gets cancelled, and therefore, what we will get that the number of electrons is equal to 5 into 10 to the power 22. Hope it is clear. I will try to explain it again. So, what they are just saying is, they are saying that because the amount of thermally generated electrons, what is thermally generated electrons? Thermally generated electron as in, if we have understood in the previous concept when we were understanding intrinsic semiconductors and extrinsic semiconductors, that when there is a change in temperature, due to change in temperature also what happens is there is an excitation happening. So, what is excitation? Basically there is an energy fluctuation happening in each of these electrons. So, if that let us say that any of these electrons is happening or present in the valence band. Okay. So, if they move to the conduction band, so what happens is because of that there would be change in the position of electron, that would only be happening if it has passed the energy gap, or if there is a change in the fluctuation, or if there is a fluctuation in the energy of a particular element, a particular electron. Okay. If it is being said that there is no thermally generated electrons, then what we can say that the complete number of electrons which are present in a crystal, or let us say in a semiconductor, will be always due to the majority charge carriers. If we are talking about a pentavalent arsenic, that means here the majority charge carriers are electrons only. If it is electrons only, that means what? That the amount of electrons which are being produced will be always equal to the number of atoms being added, because what is the complete procedure, we have understood it there also in n type semiconductor. Let us say we add a pentavalent atom, then amount we add there. So, a positive amount of free electron is being generated there, because that is the electron which cannot be supported with any of the covalent bond from the outer silicons, correct. Therefore, the amount of atoms Nd is approximately equal to what we can say, the number of electrons. Okay. Therefore, what we did here was, only because we just understood the concept what is 1 ppm. 1 ppm is 1 parts per million. Okay. ppm is parts per million. So, what is the meaning? We know million is nothing but 10 to the power 6. So, for every 10 to the power 6 atoms we have added one atom of concentration of your arsenic. So, because we have added, I just wrote it as 10 to the power 6 will give you 1 atom. Here 1 atom can be understood as 1 electron, and therefore, we can write that 5 into 10 to the power 28 atoms will give you 5 into 10 to the power 22 electrons. Fine. So, that is the thing which we will write here, and therefore, what we will get NH. So, NH will be nothing but equal to your Ni squared upon N E. So, Ni squared will be nothing but 1.5 into 10 to the power 16 whole square upon this will be 5 into 10 to the power 22. Okay. So, when you will solve it, you will get approximately 4.5 into 10 to the power 9 per meter cube. That is the amount of holes present in this will be of the order 9. So, it is quite evident, as you can see clearly, that the electrons are the majority charge carriers and the holes are the minority charge carriers. So, that is the explanation of this example here. Okay. So, hope I have explained it clearly. Let us now move to the new concept, that is p-n junction. Okay. Fine. So, let me first iterate and then we can move forward. So, p-n junction is the basic building block of many semiconductor devices like diodes, transistors, etc. Okay. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. So, because p-n junction is the basis of majority of the things we will understand in subsequent classes of this chapter only. So, it is important to understand p-n junction, so that we can understand diodes, transistors, etc., which will come in the later part of this chapter. So, we will now understand how to we will now understand how to junction is formed. So, junction is basically this is only called as junction, and how the junction behaves under the influence of external applied voltage. Please remember, this external applied voltage is also called as bias, because this is very important. We will understand majority of the topic based on this bias concept only. Okay. So, please remember that external applied voltage is also called as bias. Okay. We will understand two different things here. Just I am explaining you beforehand only. So, there is something called as forward bias, and there is something called as reverse bias. Okay. So, that is why I have explained you why there is an importance of understanding the concept or the word bias. Okay. Fine. So, let us start with the p-n junction formation here. Okay. So, consider a thin p type silicon semiconductor wafer. Okay. So, what does it name suggest? So, basically you need to consider that we are having a p type semiconductor, some sort of like this. Okay. So, it is having some very small thickness, and this is your p type semiconductor. Okay. So, let us say this is your p type semiconductor. What is the meaning of p type semiconductor? As the name suggests, p which is positive, that means the impurity added in this will be your trivalent impurity. Okay. Fine. So, consider a thin p type semiconductor wafer. By adding precisely a small quantity of pentavalent impurity, part of the PSI wafer can be converted into NSI. Quite evident. Why it is NSI here? Because we know that n type semiconductor has a pentavalent impurity, and a p type semiconductor has a n type semiconductor has a pentavalent impurity, and a p type semiconductor has a trivalent impurity. Yes, I was telling correctly only. So, now what they are just saying, that if I add a pentavalent impurity, is quite evident that this p type will have a small portion which will convert into your n type semiconductor, correct. So, it will change into n type at some places. Okay. There are several processes by which a semiconductor can be formed. The wafer now contains a p region also and a n region also, and the metallurgical junction between p and n region. So, what they are saying, that because of the addition of this impurity, there would be somewhere where this will be a p type, and there will be somewhere where this will be n type, and a metallurgical junction. So, this is that metallurgical junction between a p type and the n type. Fine. So, okay. So, let us not go into technicality much here in this chapter. In this, we will go with this in the next part of this lecture only. So, let me stop it here only, just to have a quick final revision about what we understood in this p-n junction formation. So, first of all, we understood a concept which is called as bias. What is bias? Basically, that what happens when an external applied voltage is applied to this junction. We will try to understand that in subsequent classes. And next thing we understood is that when we are trying to form a p-n junction, what we basically did was that there was a p type semiconductor, and what we did was we added a pentavalent impurity into it. Okay. So, we have added a pentavalent impurity, so that a part of this is now a p type and a part of this will be an n type, and this will be a metallurgical junction formed, which is basically a junction of p and n. That is why it is called as a p n junction. Okay. We will understand more about it in the next part of this lecture only. So, let me stop it here. So, thank you so much.